this is a conversation I had with the ANSYS people that, all right, let's start class, guys. You can stop talking and guys that we get. All right, class start. Okay, or else you can take the discussion outside. Excuse me. Class start. All right. So, the priority in ISPAC is, in the object tree, we know that you have to arrange objects based on which material property will supersede. So, we'll go over that. Now, the most important thing is, you got to create walls for boundary condition. Therefore, if you make the cabinet none, property none, then it still forces you then. You can't put boundary condition on the other objects. You got to actually create a wall. So let's now do a simple conduction problem, and then we'll go directly to the questions you have. So let's say we want to do I'll try to make the problem take notes on the methodology. So now we're go to geometry, right? And select geometry. Now we create our geometry. I absolutely would not do most of the geometry I will only do now in ISPAC, in ANSYS Workbench, even for ISPAC. Sure. So now let's just create a primitive object, so a box, right? And let's say that this is going to be a substrate, so I'll make it 100 by 10 by 100. And create it as frozen. So now we generate this. All right. Now let's now generate something else on top of this. So we create another box. And in this case, let's say we start off at 15. So that's 35, so we'll make it 70. And this was, what was this? This was 10. This was, what? So 15 and 10 and 15. And then the delta is 70, so it would be 15 on the other side. 30 and 20. And this is 70. Okay, so we created this. Now I want to create something else right in there. Right? So here is our call this something called the substrate. Molding, for example. start from 30. So that's 20, so 40. So 30 and 10 and 30. Give it 40, 10, 20. Right, and we'll say add material frozen. Okay, so if I look at this now and this view, front view, it looks like this, right?
Question.
Okay.
So when you did that, does ANSYS recognize that the molding has a cutout where that new solid is, or?
Oh, no.
Okay.
See, you're trying to ask a tough question.
Well, it won't mesh like this. It won't mesh.
Yes, it will.
Please continue.
I know, just, you know what, I can understand, you know what the problem is?
No.
You gotta have it in the right order for it to mesh. I'll show you where it would not mesh, then it would mesh.
Okay.
All right? In just a second. So this suffices for right now, right? We're gonna actually do the conjugate model later. So now we're just gonna call this module. Right? So, and your concern is the mesh, we'll get to it, right? So now let's create a new part. What the new part does is, it does what we call the, I call it partition. It partitions it. It cuts it up. In other words, to make sure that there is volumes. It takes, for example, the big solid there, who will kind of partition it, right? Now, when you go back to IcePack, the big solid on the top will still be, if you look at the geometry, you still will have the full dimensions, but we'll see now about dimensions, all right? So now, we have this. I didn't have any order. I created an any all order, right? It doesn't matter. So we formed a new part, all right? So now let's get out. File, close design model. Okay, so now this is the options we have, 3 options. So now we say file, close design model. Okay, so now I want IcePack. I double click IcePack. And I transfer this geometry. Left mouse click and drag it and drop it. All right, so now I have the geometry. I transferred the geometry. So now let's go. I don't like the way you're looking at this. I told you so. You're about to say I told you so, right?
I'll just let it happen.
All right, so now let's go to setup. So there's a couple of things you have to do to solve a conduction problem. So write this down here. I can just give you this. There is. We also need to, first of all, disable fluid mechanics. And change the tolerance. Okay, so it's just a couple of things you have to do. And then here, there's one other thing. Okay, so let's do all this stuff first. So now if I click here, I got substrate, molding, and module. So I'm saying that the way it's arranged right now, the problem you're saying is going to happen. It's not going to mesh. Because from a material property point of view, this is the correct way. I'm sorry. Let me just move this here. Let me move this here, for example, right? The molding is now defined first. I mean, the only two things is molding and modular molding, right? And the molding is defined next. Keep in mind the molding the entire module is encompassed by the molding. So the first thing we do is, let's get rid of the cabinet. So we go to geometry and say prism none. Update. Continue. So the cabinet is gone. No more cabinet. All right? So now this is the objects we have. So then we go to problem setup, basic parameters. You turn off the fluid mechanics. No flow. All right, so just temperature. And then you go to solution setup, basic settings, and you change the energy to very high, 1e, very low value, 1e to the minus 10. Now this is just for energy. This is just for conduction problem, all right? We'll get to conjugate. We'll get to your example. But you might want to do a conduction problem. For example, some of the stuff that you guys are doing for other classes, you may want to do a simple conduction problem, right? You may have a heat conduction class. You might want to do conduction, right? You may want to do that. So you do that, and then you go to advanced settings, and then here is what you have to change this to W and change this to a small value, 1e to the minus 10. I'm going to email you this. So let me just, I have this already. Let me see, I think I do. Yes, I have this right here, right? So I'll send you guys that. Okay, so now what else didn't I say? I disabled the fluid mechanics, changed the tolerance. Okay, so now I accept this. Okay. Now, is there anything else? Now we need boundary conditions. So I'm just going to put in the module, say, 10 watts, for example. 10 watts. Update, done. All right? So the module has 10 watts. Now I got to get rid of this. In order to get rid of this, I need a sink, right? So I need to define a wall. I can't, so you might say, why don't I use, for example, the wall of the molding? As an example. Here's the molding, right? Why don't I use the wall of the molding? You can't. You have to create a wall. So let me see, this is now X direction. Let me say at the small X direction, I want to create. So a trick is, so you don't have to remember, go to molding and parameterize it. It's already got the geometry, so I'm just going to call this X start. All right? I'm going to start this. Keep in mind, it's going to remember those values. All right? It's going to remember those values. This is really, I could have said molding, but that's okay. YF. That's just so I don't have to remember this stuff. CS and CF. So I'm going to tell it update. It's going to keep asking me, is this correct? Yeah, I'm going to say yes, yes. But it remembers from the, from the table what value there was. Okay. So I did that so that now I'm going to create a wall. So I'll go here to the wall. I double click it. Now I want the wall to be the same as the so this is going to be X star. I mean, I can change it. I'm going to make it XY, so it could be anywhere. So yes. So this is going to be constant. I wanted a constant X. So let me change this. So I want YZ, right? Because I want a constant X plane. I want it here and here. At the molding, oops, at the molding right here and right here at the bottom X, I want to create a wall, right? So I go back here. So I'm going to say at XS, right? And this is gonna be YS. Oops, this is millimeters, right? Millimeters. 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 All right, because that's how I define. And this is ZS. And this is ZF. And then this is YF, right? Everything okay? Okay. So created that wall right there, right? You know, you mind turning the light out if you guys can see? Might be better. Thanks, buddy. Appreciate it. Is that okay? Can you guys write still? Or is that too
Okay,
much?
that's good. That's good.
All right. Okay, so you can see here, the wall is created, right? And maybe I can change the color of the wall. So. Right there, so there's the wall. Now, once I've created one wall, now hit that wall now, it's gotta be a sink. So I'm gonna apply a heat transfer coefficient. So I'm going to say heat transfer coefficient, edit. So I'm going to say I'll put the value of 20 watts per meter squared per weekend. All right.
Interesting.
Now I have done this, I can just copy this, right? So I can now create another one. Right? And you guys remember, you can copy, right? You can copy from, yes, whatever you made before. We created a wall, so I'm going to copy that. Except the geometry, where is it going to be? Is the X? Where is it going to be located?
X finish.
XF, yes. Someone small, yes. XF,
I don't know.
right? So for update, I should show up here. So now, you know, there it is. It's already got the 20 watts per meter squared per weekend. You edit it. What happened? Properties. Oh, H. Oh, external conditions, heat transfer coefficient, edit. Why the heck didn't I remember? Supposed to remember that, but let me update, done. Oh, maybe when I copied from, you know what I did, right? I could delete this, just to check. Let's just delete this. I think when you create, because I don't like to do things the long way if possible. So when you copy, right, you want to copy object info, right? So not only do you want to get the shape info, but you also want to get the object info, right? If we do that now, it should also copy the heat transfer coefficient, right? So if I do this, now I can go to geometry and change it to XF, update. Now if I check the properties, see it's got that. And if I edit it, it's got 20, yes? So that makes sense. Now, this is, the physics says it's a heat conduction problem, and it's an elliptic problem, boundary values. I have supplied all the boundary values, right? The module, I believe, we put power in there, right? So it's certainly ready to go, yes.
What was the purpose of the wall?
Yes, the purpose of the wall, I mean, you got to put the heat transfer, you got to put the sink someplace, right? Now, you could have said, why don't I just go, good question, why don't I just go to the molding and go to one side of the molding, right? You can't put, if you put the heat transfer coefficient on that one side of the molding, unless it's at the physical extremum of the boundary, right? Like the cabinet, something like that. It would not take that boundary condition. So they're actually going to write that as a problem. So this is, it's just, so what you have to do is, you just got to create a wall so that you can put a boundary condition. Otherwise, it's going to be adiabatic. So ideally, what you would like to do is you just want to say, I want to go to the molding. I want to go to properties, individual side edit, and put that right there, right? But you can't do that. You run into errors, yes.
Why aren't we putting like the wall at the bottom of the or the the substrate? Because that would be the.
This is not about what the optimal place. For example, that typically might not be the best place. Probably if this is a PCB, for example, it will be here. The bottom probably is going to be adiabatic. But I'm not looking at the physics right now.
So does the wall actually model anything, or is it just something you have to put in for the coating to work?
No, the wall is critical. That's the
Right.
sink. This is where air, I'm just only saying, right just at these two places is the air flowing. Air is not flowing on the other side. You gotta have some sink, right? I'm just trying to have a viable problem here, right?
Okay.
It doesn't really matter. It's up to you where you put the heat transfer. Heat transfer coefficient typically, if you assume that the air is blowing, there's going to be some H here you're going to pick up if you're going to solve it as a non-conjugate problem. There's going to be some H here, different H's here. But I just happen to put the H at these two places. Heat got to go out somewhere. I've generated 10 watts, right? If you generate 10 watts, it got to go out someplace. Because everything is adiabatic. Where's it going to go? You got to give it a viable heat flow path. Yes? You get that? Would you get that? Or you have a question?
We're modeling pure conduction right now.
When you say pure conduction, from a physics point of view, it's not really pure conduction. What you're saying is, I'm decoupling the convective heat transfer from the conduction heat transfer by putting a heat transfer coefficient. The impact of the air, I did all kind of experimental work and found out that I can put an H at distance. Yeah, there's no fluid mechanics here. Remember, I disabled.
Yeah, you went in there and changed everything to make sure it was
I said
just
the basic
conduction.
parameter, no flow. So this is strictly a conduction problem. We're going to get to the conjugate problem in a second. If you understand this, I absolutely think the rest of it is just the same, right? The beauty is now, okay. Now let's mesh this. Now we're going to run into your problem. Let's say mesh. All right? I'm just going to take the default and say mesh. Warning, no mesh exists for a module body. Is that the problem we've been having?
Yes.
All right, you guys see that. Now I want you to see the order here. The reason that is, it first sees the module, right? And then the molding encompasses the entire module, right? So if you want the property of the module to be distinct, you got to move this module anywhere after the molding. All right? Now we just moved it. Now we put the molding first. Yes? And now the module is behind it. From a material property point of view, see, this is not ANSYS, this is ISPAC. The way ISPAC, this is not a solid model-based code. The solid model-based code you can just say, I'm just going to do Boolean algebra. I want to cut a hole in there, right? This is the geometry here. This is solid model-based geometry. I've cut a hole in there. You didn't cut the hole here. The way ISPAC differentiates it is, it sees this priorities. And as soon as it sees that, it says, it first puts the property of the molding throughout the entire domain. Through this domain. And then it sees this and says, oops, I'm going to overwrite all of those elements by this. And the material properties by that. All right? So the order. Now let's mesh it. So now we're just going to do the same thing. It didn't mesh, right? We run into a problem here of meshing. Now let's mesh again.
Let's,
Mesh. No problem meshing, right? Okay? And now we can just solve as well. So now you can look at the mesh. We can look at here.
that's the simple.
And now look at the mesh. You know, you can display this. And volume.
No.
And you can select the objects. Okay?
I'm not quite sure how it would work the way he's modeling
Display mesh, I'm sorry. There it is, right? So you guys see the mesh by object. Substrate, molding, there is the molding. And this is the module, right? So on and so forth. Okay? So now I'm ready to solve this.
Don't you have to add heat source first?
I did.
it. Coming.
I've not seen that.
Here. So the
Module.
had a property
10
of 10 watts.
Don't you have that the connectivity?
All right?
That's what the, I think that's the walls.
Now, keep in mind, I didn't worry about the material properties. You start fooling around with it. Right now, it's all steel. We really should go, say, to the molding. And you can just say, edit material, edit definition, oops, not that, create new material. And you can go up here, properties, and thermal conductivity. That's really the only thing that matters, right? Because it's a steady state problem. Rho CP does not matter, only K, right? So now you can change this to say
That
20,
assumption when you was good.
Yep.
Right.
That's a good assumption.
update, done. And you can go
They do that.
do that kind of stuff.
Should be able to do everything.
You know, you can
It's
change
not
the module, say, a little higher.
Yeah, I don't know. Need to ask.
Dr. Aganathan, for the wall, how did you know that the wattage was 20 for the convection coefficient?
Didn't matter. This is just something to show you how the program works. How you do that is there are correlations. For example, if you have some heat sinks and flow-aware heat sink, you can either solve the conjugate problem or you can go to look at the books. I can refer you to Sean London, for example. That's a very good reference for laminar flow and ducts. Or you can look at Winong's book for turbulent flow. There's all kinds of correlations out there that you can find, all right? So, I just so happen that I have an idea what air cooling typically is, but you got to multiply that by several factors depending on the fins, right? We typically use 2,000 watts per meter squared degree K because we have a lot of fins, you know. So then
Yeah.
okay, so we have done that. So now if I go to module and create new material, thermal conductivity, let's say, we say that's 50. I mean, silicon is 120, but I'm just, these numbers are irrelevant. All right? Where do you think the heat's going to go now?
Oh, your walls?
Right there and right here, equally, right? This is all symmetrical. So 5 watts is going to come out of wall 3, and 5 watts is going to come out of wall 1, right? So now let's just solve this. Oops. This computer will shut down in 5 minutes. Cancel. Cancel or? Yes. Good thing. All right. So now we just say solve. now I am claiming that the conjugate stuff is gonna be just as easy.
That was fast. Oh, that's why. Left foot. It's steady state, so it shouldn't move, right? That should be it.
So I could just, for example, post-process here, and plane cut. And we can do a Z cut, show contours, display, right? So you can look at it.
Cool.
Right?
That's really
Move
cool.
that around and look at different, right? So you would expect it to be hottest right there where the module is. So things, now, a good thing to do would be a report, right? Report, and you guys just got to check it, I forgot how. So you can go up here and you can say, add objects. Where's the add?
There's a new star on the right side of there. On the right side, it says new.
Oh, no, yes, okay. So, let's now check the wall. Wall, right? Wall 1. Okay? And I want all sides, it doesn't matter. I want the heat flow. All right? And, right. -5, right? So let's now add. Let's add. All right. So there it is, right? 10 watts. 10 watts came from the module, right? And 10 watts is going out, -5, right? So energy is balanced and so on. Now, let me quickly move to really, unless you guys got any